Thank you, Anne. So, NVIDIA's advances in virtual reality are everywhere at SIGGRAPH this week. You can see we have talks, presentations, demos, and what I especially want to encourage you to do is to try our hands-on demos on the show floor and at eTech, because there's a lot of things that you really need to see and to feel to understand their impact. And you can have an actual experience directly with that new technology. A lot of this is coming directly out of our research department. We have 120 scientists. They're working on all areas of computing. We have high-performance computing, visual computing, artificial intelligence, graphics, virtual reality, and we're collaborating very closely with a lot of the leading universities, and you're going to see the output of those collaborations today. When I describe them, to keep the terminology simple, when I say augmented or virtual reality, I mean them almost interchangeably, and you can include AR, VR, MR, XR, all as sort of part of a continuum, and we think in the future that distinction is not going to really be significant. So our vision for the future isn't about next year's GPU or products. I'm talking about high-risk new technology. It's just being tried out in our lab now. And we're very open. We're showing a lot of the stuff right as we're working on it at SIGGRAPH, but these are things that aren't going to be in products maybe next year. A lot of them are a ways down the road, even if they do work out as well as we hope they will. It's really hard to predict the demand for this kind of future technology that I'm talking about today. Most consumers take for granted the technology we already have. It feels like it's always been there, even though we intellectually know it hasn't. And it's very hard for people to picture completely new computing paradigms. We think in terms of this year's products getting a little better and incremental advances. The apocryphal quote that we all know is Thomas J. Watson, sort of World War II era IBM CEO, saying there's a world market for maybe 5 computers. And we kind of smirk at that now, but if you go back even to the 1970s, there were very few institutions that had high-performance computing hardware. So it was extremely limited even decades after that quote. And if you go to, say, the 1990s, and I asked you, who's going to need fast networks, gigabytes of storage, really good 3D graphics, and massively parallel compute, you probably would have thought at the time, well, that's maybe scientists or military or engineers. So in this analogy of high-performance computing, across decades, it was getting smaller, it was getting more affordable, but we were still thinking of it as a niche application until in 2017, when we think about who uses high-performance computing today, the answer is everyone. It's pervasive. This is a high-performance computing user today. And that's really significant. This happened because in 1999, Nvidia had a vision for programmable consumer graphics and introduced the first GPU. And at the time, that was extremely high risk. They were saying to a market that didn't look that different from 1997 that we think everybody in the world needs high-performance computing. And it's not going to be about scientific and medical imaging alone. It's going to be about every interaction you have with computation is going to completely be revolutionized by the power of a GPU. And today, that vision was clearly validated because we do take for granted things like the GPUs in cell phones. We don't think of supercomputing, even though that's the kind of power that they really have compared to those 1997 machines. So this is what real success and real vision looks like in the computing industry. It's changing the world by making new forms of computing not just steadily better year after year, but making those revolutionary leaps where those new forms of computing become pervasive. They become part of our lives. And today, NVIDIA Research has a vision for virtual reality, and it goes beyond the gamers and power users who are involved with virtual reality today. So who is going to use augmented and virtual reality in the future? Well, the answer is obviously everyone. That's going to be the interface to computing. In much the way that cell phones and tablets and touch screens have taken over as interfaces, we think that those interfaces themselves are going to go away and be completely replaced with virtual reality and augmented reality. And those devices are going to be not like today's head-mounted displays that look like heavy ski goggles. They're going to be lightweight, like regular glasses or sunglasses, and they're going to use lasers and holograms. And I'm not saying lasers and holograms because that sounds like science fiction. I'm saying that because those are the technologies we are using today, and we know that's how to get to these lightweight, wide field of view displays that we care about. So today's modern VR systems, and the gaming systems and GPUs that power them, they are breakthrough technology, but they're early adopter power user technology. They are mainframes, and they need to become tablets. And so I'm not just talking about the headsets, I'm talking about our goal of a pervasive new approach to computing. Now, Nvidia is really good at GPUs and rendering, but virtual reality isn't just about rendering. Virtual reality is a completely new medium from film and games that have preceded it. And when you have a new medium where it's not a renderer, it's not a game, it's not a film, it's not a GPU or an app, you need a completely new system, a new graphics pipeline for VR that ends up being completely different than games and films. And so what we're doing in NVIDIA research is inventing that whole pipeline. That's why we're using optics and new displays, new algorithms. We're using AI within the virtual reality pipeline. We're adding new sensors to the system. We're reinventing everything about the way graphics is done to support virtual reality. And that's why what I'm going to show you now, and what NVIDIA is showing this year at SIGGRAPH, is bigger than the impressive rendering we've shown in the past, because it moves in completely new directions, and what we're trying to do is this revolutionary leap to pervasive VR as a new mode of computing. So to put the future AR/VR system in context, let me first describe how the systems that are used today for graphics work. And I'm going to start with film, because that's the visual fidelity that we want. Talk about games, because that's the interaction that we need for virtual reality. And then I'll talk about the pioneering, what I would call modern VR systems that we have today, and how we're going to change from those. So first, let's look at film. Now, we all know that when we see an action film, a lot of what's on screen is 3D graphics. And that computer-generated imagery has reached the point that there are often entire shots where there's no live action footage at all, where absolutely everything is simulated, because that's how powerful computer graphics are today. And the system for enabling that level of visual fidelity for cinema looks something like this. So on the left, we have an authoring box. And there's a lot of tools and a lot of technology that go into just creating the data that feed this system. Then we have modeling primitives like particles and triangles, but also things like subdivision surfaces that are good for curves. And the renderer itself in the middle uses an algorithm called path tracing. And if you're not familiar with that, you've probably heard of ray tracing, and this is kind of like the bigger sibling of ray tracing. It builds on that. And we're going to go into that at the very end of the talk. And all of that 3D is actually followed by 2D passes that are where color grading and adjustments happen. And there's an interaction loop in film. Not interaction with the audience, but interaction for the teams that are developing these. And so what happens is that the final frames are actually, in an indirect way, coming back and affecting everything that's happening. And there's a lot of innovation around trying to shorten that loop, not to reduce the time to produce the final cut of the film, but to reduce the intermediate interaction. So games essentially took this film system, which had been evolved over decades, and they moved it to real time. And the way that they did that is to essentially replace the path tracing box with a rasterization box, but there's still authoring, there's still post-processing, there's still display, and there's still a developer feedback loop. Now, the authoring process is incredibly important, and authoring for VR is another really important step, and it's something we're looking at. But today I want to focus on the software-hardware interaction boundary, and so I'm going to set aside authoring for the rest of the talk. So if I do that, we're left with the game graphics pipeline. And there's, of course, this crucial interaction loop. That's what makes the game a game, where the image on the screen affects the player makes a decision, and presses a button. And once the player presses a button, there's some input that goes into the game system, and it affects a frame that's rendered downstream. The amount of delay between when you see an image and press the button and when the next image that's affected by that happens is called latency. That's how long it takes for a full trip around the system. And in some cases, the latency might be multiple frames. For a game to be responsive feeling today, it has to be under about 150 milliseconds. So as I said, instead of path tracing, the renderer for games is based on rasterization. What I'm showing here is a deferred shading rasterization system. And that's what's been developed to give today the highest visual fidelity and throughput. The challenge with the deferred shading system is that it also costs you latency. It costs that delay between when pixels go in and come out of the pipeline. And each of those boxes costs some time to process, and then the red lines between them are synchronization barriers. And what happens at the synchronization barriers is there's a downstream unit that can't process the first pixel of the next part of the pipeline until the previous stage has processed the last pixel. So for example, we can't render lighting until we've completed computing the shadowing. And so the latency is increased every time there's another one of those boxes, and it's increased substantially every time there's another one of those red bars. And this distinction between the processing power and the delay is very important. So if you think about an assembly line, which is what this GPU pipeline is, you can have cars, or in this case pixels, coming out of a pipeline very quickly, but for an individual pixel or an individual car, it could be in the pipeline for a very long time. So those are independent, but they're tied together by the way we design these systems. So this pipeline can, of course, deliver amazing 3D experiences. And in fact, with careful art direction, video games can now approach the quality of films. In fact, the primary difference between, say, the Star Wars video games and the Star Wars movies isn't the peak visual fidelity of an individual frame. It's about how much artist work is needed to go into the fact that we don't have true light simulation for games. So games tend to be a lot more static because they have to be manually lit for a lot of the scenes, and we can't have quite the level of epic set pieces. Or if we do, we start losing visual quality and the lighting won't be correct. So that was film, and film migrating into games. And that was an evolutionary step, and they learned a lot from each other. Well, games then very recently evolved into VR pipelines. And so when game developers wanted to get to modern VR system, what they did was they took the existing game engines they were working with, and they had to somehow hit the incredible specification increase for a modern VR system. So a game today needs to be able to process about 60 million pixels per second. And that gives you a 30 hertz HD game. But when you go to VR, you need to hit about 450 million pixels per second. So you need to somehow get 7 times an increase in total pixel throughput. And obviously that's going to come out of visual fidelity. But actually, even more challenging is that 150 millisecond latency that was acceptable for video games is not going to be acceptable for virtual reality. And in fact, we need about a 7 times decrease on latency, even as we're trying to get a 7 times increase in throughput. Let's look at latency first. So since the latency was caused by the number of pipeline stages and the number of synchronization points between them, the first way to attack latency is to say, well, let's just throw out some stages from the pipeline. And that's, of course, what everybody did. The problem is when you throw out the stages, you end up having a huge decrease in visual fidelity. And so when we got to virtual reality, we had wonderful interaction, wonderful immersion, but our graphics took about a decade step backwards in terms of the visual fidelity. This lets you hit frame rate, and it brings down the latency, but it turns out it doesn't quite bring down the latency enough. Just getting through 1 or 2 of those boxes still takes too long. You have too much lag in the simulation. And so a really key technology for unlocking latency is called time warp. And the idea of time warp is that we actually add another stage. We add something expensive at the end, but it's really close to the display. And what we do is we allow the renderer to produce an image that has too much latency. The image is lagged, it's a little bit late, but the time warp step takes data directly from the tracking information on the head and feeds it right into the end of the pipeline. It doesn't go through the whole renderer and the virtual camera. And what time warp will do is actually warp the image so that it moves to match where I'm looking pretty close to the time when it's going to be displayed, as opposed to where my head might have been when we started rendering the frame. And with a little bit of prediction on that, you can get down to between 50 and as low as 0 milliseconds of latency. And that's really what makes modern virtual reality possible in terms of latency. Another key GPU rendering idea for VR hardware is lens distortion. So if you have a good camera, like an SLR with a telephoto lens, there's about 5 different physical pieces of glass in there as a bare minimum. And those are very expensive, and they're very heavy, and they're very large. So to get a good optical system in an HMD, you would have to strap essentially 2 big cameras to your head. You would have that kind of giant barrel sticking out. And that's not really tenable. And so what we do instead is you have an inexpensive plastic lens that has a ton of distortion on it. And you use the GPU to pre-distort the image. So you account for barrel distortion, chromatic aberration. The renderer is actually producing the image on the left, but when viewed through the optics in the display, you get the correct image that's perceived by the viewer. So that's our modern VR system. So we took games, we took their pipeline, evolutionarily stripped it down, and then added time warp and lens distortion at the end. And that's the current state of the art. So to sum up where we've been so far, virtual reality is going to be the new interface for computing for everyone, but it requires a new graphics system. It's not just about a new renderer. It's about reinventing everything about the way graphics works. And today, the Pascal architecture, I've talked about the software, but on the hardware side, there are special features in Pascal designed to accelerate virtual reality. It can preemptively multitask the time warp so that we get extremely low latency. You get stereo rendering, so both eyes can be produced at the same time. We don't have to run the pipeline twice through for 2 eyes. And there are a lot of features between the software and the Pascal architecture that reach the power users. So we're there. We have the breakthrough technology. But now we need that revolution. Now we need a non-incremental jump. We need a huge leap in computing power and visual fidelity to get to future VR. So I'm now going to describe work that's been done in our lab and with our collaborators at various universities around the world. And we're not trying to drive a display. Our goal is to drive the human visual system. And so our specifications don't come from screens and projectors. They come from human beings. And there are a lot of ways of measuring human perception, but let me give you within like a factor of 10. So you start with the field of view. You can see about 220 degrees horizontally and about 135 degrees vertically. It's about twice in each dimension what we're seeing with current head-mounted displays. That's a big leap. You can resolve thin lines down to about 1/60th of a degree, and that's if your eye is fixed. When your eye is moving, and especially for jagged edges, it's closer to about 120th of a degree. So that's an incredible resolution the eye is capable of. And when you multiply those together, you realize you need a resolution that's about 200 HD TVs somehow attached to your head. So that's a big jump. Right? I was worried about the 7x increase we're going to need to get from games to VR, and then here comes a 200x increase. Actually, it's a little worse, because games today are 60 or maybe 90 hertz. If you want to get rid of the strobing and blurring in VR, you probably want to be up somewhere around 240 frames per second, which means if we're at 450 megapixels today is what modern VR systems are pushing, we need to get somewhere in the region of 100,000 megapixels per second. These are huge numbers, even compared to the incredible computing power of today's machines. And of course, it's even a little worse, right? So we probably want high dynamic range so we can have really bright brights and really dark blacks. And we'd like to, if we're talking about the ideal, where can we really get with the human visual system, we want the visual fidelity comparable to film. And for reasons I'll explain in the last couple of minutes of the talk today, I think that's about a 10,000 increase if you just went for brute force raw horsepower. So this is pretty big. And then we start getting at, well, I'd like to focus into VR smoothly and all these other features and have haptics. And you end up about 5 or 6 orders of magnitude off. And I think at that point, it doesn't really matter if it's 5 or 6 orders of magnitude, right? We need about a factor of 1,000,000 in the experience, to hit human specs, to hit the limit where it's not worth trying to improve graphics anymore. So we have about a factor of 1 million to go from today. Well, there's a couple tricks we can use, and I'm going to try and start knocking down that factor of 1 million. There's still going to be a big factor left at the end, but that's what we're working on in NVIDIA research. And the first idea that you might be aware of is that while we need 200 HD TVs to really fill our field of view with enough resolution that you don't see any pixels, you're probably aware that your eye doesn't have uniform resolution. So wherever you're looking, the center of your eye, the fovea, has that resolution. But as you get outside the fovea towards the periphery, we have relatively low resolution vision. We're sensitive in other ways, say to flicker and to sharp edges. But what if we take the game pipeline and instead of rasterization, we use foveated rasterization? What if we match the resolution of the output to the resolution of the human eye? And the trick with that is if you just take that idea, say in this classroom scene, imagine that this is the field of view of someone who's in a head-mounted display in virtual reality and they're looking up at the clock. Then we know that, say, over on the bulletin board on the left side, we don't need very much resolution. But unfortunately, you can't just render it blocky like that, because those jagged edges and the flickering that happens with the jagged edges and the loss of contrast that happens from blurring out the image is perceptible in subtle ways. And what we found is an algorithm that will actually predict the exact amount of blurring and contrast enhancement we need so that you can't perceive the fact that the periphery is low resolution. So foveated rendering isn't just about dropping resolution, it's actually about changing the quality of the image in very subtle ways. So that's one thing we can do to start cutting down our resolution. Let's look at other places in the pipeline. So games today are primarily driven by points, particles, and triangles. But there are a lot of other primitives that are known to computer graphics. Maybe we can start experimenting with those. So for example, in this work, in addition to the triangles that are modeling this dining room kitchen scene, we also have captured all of the light in this virtual scene. It's something called a light field. And it's capturing at every point in every direction the amount of illumination passing through. And what we can do is use that to light the scene itself. And so all of the reflections that you're seeing here are extremely realistic because they're being pulled directly out of that light field. So this idea of capturing light not just maybe on surfaces but at multiple angles can be used in a few ways. Here we're using it as a new input primitive to a graphic system. But what if we also used it as an output primitive? Because you see there's a really big problem with today's virtual reality and augmented reality displays. They all assume that you're focusing about 1.5 meters in front of your face. That's what the lenses are doing. They're optically moving the display out far enough that you can comfortably focus on it. And the image looks good if what you're trying to look at in the virtual world is actually at 1.5 meters. But there's a problem. If you look at something that's very far away or very close up, then your eyes are converging based on the virtual 3D point, but they're still focusing at 1.5 meters. And that difference between where you're focusing and where your eyes are converging causes significant discomfort for many users. It's one of the main problems with virtual reality displays today. And the second part of that challenge is that in VR, it's discomfort. If we are in an augmented reality context, you're looking at a real object in the distance, and the display is at a fixed distance close to you. What will happen is when you're looking far away, the augmented 3D graphics or text or whatever the overlay is too blurry to read. It's not useful. It's only useful if the virtual distance matches the physical distance. So this focus problem where the convergence and the focus are at different depths is a huge problem for today's displays. And one way we've tackled in the past was using that same idea of light fields. So for this display, what we were doing is the GPU is producing that image that you see in the middle. And it looks like sort of a bug's eye view of the world. And that's one possible representation of a light field. And we use that light field, in this case with special optics, so that you can perceive the image that's shown on the far right. But what that's doing is it allows you, because it captures all of the light in that funny looking representation in the middle, it allows you to focus naturally into the image. This was a really breakthrough idea because this is one of the first times where the graphics system is not outputting an image. The graphics system is outputting something different. It's feeding data to a display, and there's effectively computation on that display that then gives you the image. And we think this idea of bringing computation closer to the head, closer to the visual system, is going to be a real key breakthrough idea for virtual reality. So this is what we were showing a few years ago at SIGGRAPH. This year we have two new solutions to this problem based on that same idea of let's bring computation right up into the display. And maybe we can do that in a way that's more efficient than our earlier ideas. So what I'm showing here is a variable focus optical system for augmented reality. And you can see this in eTech right now and try it out for yourself. So it's variable focus. We call it varifocal optics. And ignore the sort of science fiction looking setup. That's just part of our experimental configuration. What's important are three pieces of this display. So one is the thing that looks like a flat sheet of glass is actually a hologram. The second is the thing that look like lenses are not lenses. They're effectively just curved sunglasses. And because of the way we built the system, they have those thick rims on them. But they could eventually be as thin as the sunglasses you wear every day. And the third piece, there's actually a laser. And when I promised you lasers and holograms, this is one of the examples. And the idea is that the laser projects an image down onto the inside of the curved sunglasses, and then it reflects back into the hologram. And what's amazing about that hologram is it's designed so that when you look through it, it's just a clear piece of glass and you can see the rest of the world. But when the laser image comes back at it from bouncing off of the reflector, it acts like a screen. And so it allows us to put a screen very close to the eye without having to have any heavy, thick pieces of glass. We effectively have two things that can be as thin as sunglasses. And then by varying the distance between them slightly with a tiny motor that's tightly coupled to an eye tracker, we can allow you to focus naturally. So here's another version. This is with researchers at UNC, the Max Planck Institute, and Saarland University. And you can also see this one today in eTech. And it's based on a similar idea. Instead of moving the reflector forward and backward, maybe we can cause the reflector itself to be a flexible surface, so we can bend it. And you can think of that sort of like a magic bifocal, where instead of having two different parts of the lens itself can dynamically change shape very quickly. And it actually isn't just optics that we're making flexible. Input devices can also change. So in collaboration with researchers at Cornell, we've built an augmented Vive controller where it can actually change its shape. And this is almost impossible to describe. You just really have to try it. And so you can see that at eTech as well this year. And you can actually feel it shifting under you, and it can simulate different objects or simulate motion of what you're holding in VR. So this is a completely new output format. It's not just about eyes and ears anymore. It's about your hands and about what you're feeling. So what about the latency problem? Today's modern VR systems are just barely hitting sort of our minimum spec for latency, but it's nowhere close to where we'd like to be in the long run. We have a number of different strategies for attacking this within the graphics system, and some great research on them that's already been published. So one idea is recognizing that once we have computation that's up close to the eye, that's in the display itself, maybe we can break the rendering pipeline. Maybe we can take parts of the rendering pipeline that are latency sensitive, like the actual pixels you see in the final image, and separate them from parts of the rendering that might not be quite so sensitive to latency, like all of the indirect lighting in the scene and the shadowing. And so we built a system to do exactly that. And under this model, you have a wearable Tegra chip. So this is our robotics mobile chip. And we can put that inside of a head-mounted display as well. And it can directly drive the graphics on the display. But then we can tether it to a local GeForce card. So you have your full gaming rig, and it can be powering all of the lighting for the scene. And then the actual pixels that you see are being quickly updated, communicating some of that lighting data. Or in fact, what if we took that one step further? So we actually modeled using the Cloud Grid platform with the Tesla GPUs. And we said, well, let's do all of the lighting up in the Nvidia Grid cloud, and then we can stream that down. And the neat thing about that is if you're in a multiplayer environment, and if we're talking about pervasive use of augmented and virtual reality, that's where we want to be. We want to be in a world with other people, with interaction. Then we can even better share that information across all of the users because we're already computing it off in the network. And then compute some other data on the GeForce, and then finally the pixels at very low latency and the Tegra. But you know what? Maybe we don't even need the GeForce. Maybe we can break that tether and go directly from the cloud, somehow compress that lighting data down, and have a completely wireless head-mounted display experience, but that has the visual fidelity of an entire server farm backing it. So another approach for latency is let's look at the time warp and the varifocal, and let's think about ways that we could, instead of rendering at, say, 90 hertz, because that limits, if we're rendering at a frame rate, that limits how fast we can update the image when you move. What if we instead said, well, how high can we crank that refresh rate? So maybe the graphics system is still running at 60 or 90 hertz, but the actual pixels that are being time warped, they could be done asynchronously at a much higher rate. And I don't mean asynchronously also at 90, I mean asynchronously at like 16,000 frames per second. Here's an example of a prototype of that. We built this in collaboration with UNC. So what you're seeing, and you're seeing it in slow motion because otherwise it's too fast to tell what we're doing, is on the top, the 60 hertz renderer is feeding effectively a 60 hertz time warp computation. And we're projecting, we're creating an image of a checkerboard and trying to line it up with a real world checkerboard as a test. And what you see is as the camera moves, they slide off of each other because there's just too much latency and the virtual objects can't track the physical objects. But what's happening on the bottom is we're still running the renderer at 60 hertz, but now we're running the time warp-like process at 16,000 frames per second. So we have a projector, in this case, that's updating at 16,000 frames per second. And it turns out when you're going that fast, you don't need a lot of information in each frame. In fact, each frame can be reduced to binary. It's just black and white frames that we're slamming out as fast as we can, and over time they average out to the right colors. And you can see that we're almost perfectly tracking at that point. The virtual checkerboard just disappears into the physical checkerboard. Let me show you a trace of that on an oscilloscope. So the top line, when that jumps up, the green line jumps, that's the time at which the head started moving. Time is the horizontal axis. The bottom line is when we actually emitted light from the projector that matched it. And so when you see the jump in the bottom line, the delay between the top and the bottom is the latency. And our latency is 0.8 milliseconds. Not 8 milliseconds, 0.08 milliseconds. That's 500 times better than a modern VR system. So this is an incredible speed up in latency. That effectively solves the latency problem if you could integrate that with the rest of the system. And we're also looking at, well, instead of doing that time warp just on image data, just on RGB, what if we have RGB-Z data? What if we have depth? So at every pixel, we have a 3D point and a color. Well, since we have computation on the display, we can actually re-render that frame moving not just in 2D for rotation, but a full 3D translation and zoom. What I'm showing on the left is a prototype we've built of an actual system to do this entirely in hardware. So this is based on an FPGA. It's running our super time warp using full 3D points, not just color images. And then there's a photograph of what that looks like when you sort of look through the lens. But of course, your actual perception when you're wearing it is closer to the farther on the right because you don't see all that lens distortion that's compensated for. So Pascal is the fastest ray tracing processor in the world. We can hit about 1 billion rays per second. That is just about fast enough that you could replace the rasterizer for sort of simple primary ray images. And you could probably replace the shadow map box up there as well. So for VR, if we unlock the pipeline, what can we do with that incredible ray tracing power for virtual reality? Well, an interesting thing is if we're tracing the rays, we can completely get rid of the shadow maps, which means we get rid of all the latency associated with the shadow maps as well. And ray tracing can natively render red, green, and blue separately, which means we can directly render both the barrel distortion and the chromatic aberration of the lens distortion, so we can get rid of the lens distortion phase of the pipeline as well. And in fact, when you're ray tracing, you don't even need frames. So we could actually render each pixel just as it goes out to the display, rather than rendering whole frames and having the latency of synchronizing the renderer with the display. So if you switch to an entirely ray-traced pipeline, you eliminate all of the things that are causing latency, and then we have our super fast time warp on the end as well. So that's essentially a latency-free graphics pipeline that may be possible if you could power it with ray tracing. And the good news is because ray tracing doesn't have a single projective plane, you can make the field of view as wide as you want. One of the challenges today in virtual reality is that with a single projection under a rasterizer, we can't go too high above 90 degrees. We can't even hit a 180-degree field of view. Pascal has some technology to kind of fragment and wrap around the field of view. With a ray tracer, we could just do a full 360 directly. Ray tracing also natively supports mixed primitives. So in addition to triangles and particles, you can directly ray trace the light fields that we were using in those two different ways. And you can directly ray trace voxels, and we're even looking at ways of ray tracing text directly. So recall that the quality of offline film was based on an algorithm called path tracing. And I said that was like the older sibling of ray tracing. Let me explain what I mean by that. So if we go to a film rendered image, at every pixel, we need to cast a ray through that pixel to find out what we can see in the scene. But then in order to compute the shading at that pixel, we have to cast a second ray up to see if we can observe the light. So is that point in shadow or not? So you don't just, when you have those billion rays per second budget, you don't just spend it on the primary rays. You also need to pay twice as much to get to the light. Except not all the light is coming from the sun. Some of the light is also reflecting off of other objects. So we cast another ray out so that we can see how much light's coming in from other objects. But the other objects themselves could be in shadow, so we need to cast another ray off of them. And they could also have some indirect light. And this process kind of keeps going recursively. And you end up with a bare minimum of you need about 10 rays for one path at one pixel in order to get reasonable lighting. Well, that's sort of reasonable. It cuts your budget down a little bit. But the problem is, if you only cast one ray at each pixel, you get an image that looks something like the right. It's extremely noisy. And that's because we only measured the indirect light with a single ray. And so depending on where that ray went, it might go someplace dark, it might go someplace bright. The way that film solves this problem is they just keep casting rays. So the problem with that is if you get about 1,000 paths per pixel, and each of those paths has about 10 rays, and then you do some cleanup, you get those really high-quality film images. Remember that missing factor of 10,000 I was worried about in the visual fidelity? Well, that's where it is. So we need about 10,000 rays per pixel if we're going to try and brute force rendering the way that film does on top of path tracing. So we'd like to get that kind of visual fidelity without that kind of cost, just the way that we use foveated rendering and other techniques. So one technique we can do is explore, can we make the process of computing a noisy image like that and turning it into a perfectly smooth image like that? Can we run that in real time on a GPU? And we have 3 different advances this year that we are presenting this week at SIGGRAPH. 2 of them are based on the graphics horsepower of the GPU. We've built this incredible image processing machine, so why don't we use it to do denoising? The third one is based on new technology, which is that we also now have incredible artificial intelligence, deep learning processing on the GPU. And so this denoiser is actually using an AI approach to denoising, and it's learning what's the perfect filter. And we're continuing to evolve and train these ideas. But this opens up a whole new regime of maybe it's possible to get not just really low latency, really high frame rate images for VR, but maybe we can have it all. Maybe we can get film quality rendering for VR as well. And this is particularly exciting in Nvidia because it takes 2 areas in which we've really excelled, AI and computer graphics, and puts them together. And in fact, this year at SIGGRAPH, there are 4 different examples we're showing of places where we can use the AI horsepower of the GPU to also power graphics at the same time. And that goes into places like animation, as well as all of these different forms of lighting. So let's step back and look at all of the places that Nvidia is innovating for a future VR system. We started with the modern VR system today. This is the software and hardware and HMD that you can go out and buy. And then I said, we can't just evolve from this. So I showed ways that we could essentially replace this whole cloth. And this is what we end up with as a potential future Nvidia VR system. So we've spread computation right into the cloud and up onto the head-mounted display itself. We've removed almost all of the synchronization points. Because of that, latency is reduced 50 to 100 times compared to modern VR. The images potentially have cinematic quality through path tracing and real-time denoising. It's a 100x perceived increase in resolution, but thanks to foveation and eye tracking, we don't really need to render every one of those pixels brute force. We can do it intelligently. You can focus naturally at multiple depths in both virtual and augmented reality, and we're blasting potentially binary images out of a projector so fast that they become indistinguishable from reality when it comes to tracking. And of course, a key idea behind this and a key constraint on everything we're doing is the optical system is not just going to have this high quality and this wide field of view, but it has to be light, it has to be comfortable, it has to have enough power to run all day. And we're able to approach those through ideas like using holographic optical systems and laser projectors. And there's also going to be realistic force feedback and full body tracking. So with all of these features, this is a system that you really could use all day, that really can become part of your life. So in the same way that you can't imagine a mainframe computer being something you use to manage your social life, for work, for entertainment, for reading, but you can't imagine a cell phone not being that device. It's really about finding those revolutionary leaps in VR so that we can do the same thing. Right now, VR is a special power user destination activity, and we think it's going to be a pervasive activity in the future. It's going to be all of computing. You're not going to say you're using VR because, of course, you're using VR. It will be everything. It'll be transparent to you. In conclusion, VR will be the new interface to computing for everyone. Today, the Pascal architecture upgrades the gaming system to the modern VR system. But what NVIDIA is doing in our research labs is innovating for a revolutionary new future VR system. And that's through the computational displays, light fields, foveated rendering, path tracing, denoising, and all of these great technologies. Thank you very much.